So welcome to Lesson 2 in Unit 2 Combinations, which we're still in the combinatorics module. We're talking about how to count things. And we want to talk today about combinations specifically. We looked last lesson at Venn diagrams, which is a way of counting when we don't care about order, but we just want to know how many elements there are in different sets. In this lesson, we're going to look a little bit at how to use calculations, like buttons on your calculator and methods of calculating to find different combinations of things. But just as a little recall, we did talk about this in the first lesson in permutations, but permutations are arrangements where order matters. So we can talk about order in time, like first place, second place, third place, or completing something in order, like first I'm going to pull out a card, then I'm going to spin a spinner, then I'm going to roll a die. So time order there does matter. Or spatial order, where you're arranging something on a shelf, or you're arranging numbers in a row to make a phone number. In those cases, order matters and order makes a difference to the outcome. But we're going to look in this unit at when order doesn't matter. So combinations are ways of counting outcomes where you're just making a selection. You're choosing or you're grabbing things where order doesn't matter. So you've got a bag of 20 marbles, and you want to choose 5. You just want to reach in and grab out 5 marbles. And then when you open them and look at them in your hand, you don't care what order those marbles are all arranged in your hand. You just want to know, how many different ways could I reach in and grab 5 marbles if I had a bag of 20 marbles? Okay? So this is where combinations is different, because once I've grabbed them, I don't care what order they're in my hand. I just care how many ways can I grab them.
Yeah.
Okay?
Another good example is card games. You know, if you like to play euchre, if you like to play say cribbage, the order that you hold the cards in your hand doesn't really matter.
No, you change
at
the
all.
order anyway as soon as you receive them. Yeah.
The order doesn't matter where you hold them in your hand. All that matters is the combination of cards that you have in your hand.
Yeah.
And I haven't used combination lightly. I haven't used that word lightly because that's what it is.
Yeah.
Who cares about what the order is? It's just a combination.
Yeah.
So a lot of card games will make use of these. Yeah. By way of example, let's kind of walk through the relationship between permutation and combination.
Yeah, so let's use a small number and let's build up a logical progression so that you can see how permutations and combinations are different and similar. Okay.
So we got the word help, and we want to select 3 letters from this word. Again, order doesn't really matter. We just want to select. So imagine that you've got H-E-L-P, and they're all in Scrabble tiles, and you put them in a bag. How many different ways can I reach in and just pull out different selections of 3 letters?
Yeah.
Okay. I could pull out an H, an E, and an L.
So essentially you've left the P in the bag.
Yeah. Or I could pull out an H, an L, and a P.
You left the E in the bag.
Or an H, an E, and a P.
Left the L in the bag.
Or an E, an L, and a P.
Left the H in the bag. So essentially it's how many ways can I leave one letter in a bag?
Yes. There are 4. There are 4 ways to do it. The order of these things doesn't matter. Now, we could say, hey, let's look at how many ways we can arrange 3 letters from the word help.
If order mattered, and I went to reach into the bag, and I've got 4 to choose from, and I choose one and I put it there, and then I reach in and choose the next one, and reach in and choose the next one, we're basically saying I've got 4 choices, but only 3 spots. And this should remind us of our NPR.
Hey, this is a permutation where n is equal to 4 and r is equal to 3, and of course 4p3 is 24.
24.
Okay?
Yep.
So there's 24 ways of permutating 4 letters through 3 spots.
Yep.
Okay.
And there's 4 ways of just grabbing 3 letters if I don't care what order they're in.
All right. So now this is the ultimate connection between the two.
Yeah.
Right? Because we've said that permutations and combinations are linked somehow.
Yeah.
So each of these permutations that we had in this first little section of this example, each of these combinations that we've taken, well, how many ways could we arrange these 3 letters?
3 factorial ways.
Okay. How many ways could I arrange these?
3 factorial.
Yeah. These ones, 3 factorial. These
so
ones,
there's
3 factorial.
4 times 3 factorial ways of arranging them.
Yeah.
Right? And selecting them.
Exactly.
Okay.
So if I have 4 ways corresponding to 1, 2, 3, 4 of 3 factorial arrangements, lo and behold, I get 24. Okay.
Now, what we didn't tell you in permutations is that not only are you arranging the 3 letters from the word help, but you're selecting and then arranging. And
Mhm.
that's what that NPR, that 4P3 means, is that of the 4, select and then arrange 3.
Yes.
So what if we don't care about arranging those 3, or what if we don't care about the arrangement of those 3? We just want to have the select part.
Yeah.
Well, just like when we couldn't distinguish between like numbers or letters that are all the same in the last unit, we just divided out the number of indistinguishable arrangements. These arrangements, they're
it's
not
that things are
indistinguishable.
We just don't care.
We don't care about their arrangements.
Yeah.
So we're still going to divide them out.
We still want to divide them out. So we take our permutation. We take our 24, our 4P3. We take our permutation, and we divide out for the number of ways that we can arrange each of those permutations, which is 3 factorial.
Yeah.
And we come to the combination.
Which is what we got when we did it with a list.
Now, if all of this seems like a little bit overwhelming and, oh my goodness, how am I going to apply it? Don't worry, because at this point we now introduce our formulation of what the combination is.
Yep.
And it's basically the permutation divided by the number of ways of arranging each of those selections. And that's a combination.
Now, in your calculator, you've got an NPR button, but you also should have an NCR button. And what this means is it's N choose R. So we're choosing, but not arranging. And so your calculator is going to perform NPR divided by R factorial when you choose the NCR button instead. Because we're saying, I want to choose R items from N, but then I don't want to arrange them. I don't care about the arrangements, so we divide it out, the number of arrangements.
So here it is. The number of combinations of R objects chosen from a set of N distinct objects is NCR.
Yep.
Okay. We can also write it as CNR. This is a lesser written form.
Yeah.
We can also write it in big brackets with an N over top of an R.
This is the most common way.
This is the most common way, is N over top of R in big round brackets, no line. So it's not a fraction. It's not a fraction.
And it's pronounced N choose R.
Yeah. This is another way in factorial notation of writing a combination. You'll see that this right here, N over N minus R factorial, is just the permutation divided by R factorial.
Yeah.
Okay?
Yep.
Let's do some examples.
Let's see that now.
Okay. How many ways can the following cards be chosen from a deck of playing cards if order of selection does not matter?
Doesn't matter. So we don't care about the order, so we know we're dealing with combinations. There are 52 cards in the deck altogether. If I want any 4, then, I've got a pile of 52, and I want to choose 4 from those 52.
So what we get is 52 choose 4.
You type it as 52C4 in your calculator.
We could also write it as 52 factorial divided by 4 factorial times 52 minus 4 factorial.
Yep.
And what we get is, of course, 270,725.
So that's how many 4-card hands there are.
Now, 4-card permutations, there would be tons more.
In fact, you'd multiply that by 4 factorial. Yeah.
But we're not going to.
We're not doing that.
How many ways could you select 4 diamonds?
All right, so now, you know how for A, we had a pile of 52 cards, and we wanted to take 4 of them. If I want 4 diamonds, my pile that I'm choosing from is no longer 52. How many diamonds are there in a deck?
There's 13.
Okay, so that means my pile is 13, and I'm choosing 4 out of those 13.
So a much smaller number.
Yep.
13 choose 4 is 715.
So,
and we got that just from our calculator.
Yeah, 13C4, using that button.
All right, so let's look at something a little bit more advanced. 2 kings and 3 queens. So again, now we're incorporating the numbers and
I see the
or.
word and. I see and.
Same as before. 2 kings. Well, how many kings are in a deck?
Okay, so you've got 4 kings altogether. So that's a small pile.
Yeah, so that's a small pile.
Yeah.
So how many ways can I choose 2 kings?
Well, there's 4 of them, and we want to choose 2. That makes sense.
Well, there's also 4 queens, and we're going to choose 3 of them.
Yep.
So I could choose, I could say 4 choose 3. And because we've used the word and.
We want 2 kings, and we want 3
And
queens.
we want 3 queens. Yep. We're going to multiply these out.
Yep.
Again, fundamental counting principle in play right now.
Yep.
And we get 6 times 4. There are 24 ways of choosing 2 kings and 3 queens.
Yep, from a standard deck. There you go.
what about 2 spades or 3 hearts? And again, we see the word or and we think, okay, what does or mean?
Yeah.
Additive counting principle, we're going to add.
Yeah. So we want 2 cards or 3 cards here, basically is what we're saying.
Mm-hmm.
So spades, there are 13 of them and I want 2.
Mm-hmm.
Hearts, there are 13 of them and I want 3. So we're going to take our 13 choose 2 plus our 13 choose 3. And again, in your calculator, just type 13C2 plus 13C3 for your combinations, and you get 364. Ways of getting 2 spades or 3 hearts, if those are the 2 things that would get you a winning hand, one or the other. All right, this is a good example. Example E is kind of nice. We want 4 aces, definitely. We want 3 kings, 2 queens, 1 jack, and then 1 other card that is not an ace, a king, a queen, or a jack.
Yeah.
Okay.
So basically, the way of choosing 4 aces, there's only 4 of them.
So it's a small pile, and
so
we want all 4.
And we want all 4, so it's 4 choose 4.
Yeah.
The 3 kings we've seen before.
Yeah.
It's 4 choose 3. The 2 queens is 4 choose 2. The 1 jack is 4 choose 1.
Yeah.
And if we want 1 other card that is not an ace, king, queen, or jack, then we take our 52 cards in the deck and we just subtract out the aces, kings, queens, and jacks.
Yeah.
It leaves us with 36 cards in the deck.
Yeah.
And we only want 1 of them.
One of them.
So we're going to say 36 choose 1, which is, of course, when multiplied together, a pretty large number. Because we get 1 times 4 times 6 times 4 times 36. And we get 3,456 ways of choosing 4 aces, 3 kings, 2 queens, 1 jack,
and something else.
All right, here's example number 3. We have these 5 students, Eunice, Beauregard, Clyde, Hank, and Delilah. And they're being considered for a committee. How many ways could they be chosen to fill the positions of president, vice president, and treasurer? Now, president and vice president are very different roles.
Different roles.
And so having different people in those different roles is important.
Yep. And if I were to say to you, all right, everybody, I'm choosing president now, then it would matter to you if your name was pulled first, if you wanted president. If you wanted to be treasurer, that's all I wanted to be treasurer, and they were doing that third, then it would matter to you that your name is pulled third. So what's interesting is we've put one of these in here, but this is to show you as a comparison. When you're choosing roles and you're filling those positions, then order matters to the people who are being selected because they want a certain position. This is actually a permutation.
And this is what's going to start happening is that you're going to be presented with problems that could be a permutation or a combination, and you're going to need to distinguish between which it is.
The two. Yeah.
So this is one of the ways of telling. If there's specific roles and there's people that are going into those roles, order is important.
Yep.
This is a permutation. So basically, order matters here. And so what we'd say is, hey, president, vice president, and treasurer, there are 5 options for president once that person's in place, 4 options for vice president once that person's in place, 3 options for treasurer, 5 P3 ways, which is a total of 60 different permutations that they can be chosen to fill president, vice president, and treasurer.
Yep. So this committee has roles. But
yes. However, let's say of the 5 students, I want to form an executive committee. I want 3 members on that committee, but they're all going to be equal.
Yep.
So the order that they're in the committee doesn't matter. Yep. It's just a committee of 3.
Yeah. And they're going to do everything together.
What this should say, and what this should distinguish for you, is that when we're choosing committees, order does not matter.
No.
And so this is a typical giveaway for a combination rather than a permutation.
Yeah.
So here, I don't have 5P3, I've got 5C3.
Yeah.
And that's, of course, 10. Only 10 possibilities as opposed